much to the organizers for for inviting me here. It's my first time in Taiwan, and I really liked it, and this has been a very nice conference. So thank you very much. Let me just, before I start, let me just mention the set of papers this is based on. So this is what I'll say today is largely based on joint work with Kyriakos Papadimos, who's at CERN in Groningen, but also other younger collaborators, including a student, Sudeep Ghosh, and a postdoc at ICTS, and now faculty member Prashant Samatre, and a postdoc at Groningen. Before I start my talk, I just want to give you the context of what I'll talk about. So the context of what I'll talk about is that, as many of you know, there's been a revival of interest in the information paradox. Sometimes there are these debates on the firewall, but these debates on the firewall are really debates on the information paradox. And one of the points I want to make in this talk, in this first part of the talk, is that these recent versions of the information paradox can really be phrased as some kind of an existence question. And it's an existence question of the following kind. The best understanding we have of quantum gravity uses AdS CFT. And there's a question of whether AdS CFT can describe the interior of black holes and can describe the experience of an observer who falls into the interior of a black hole. And this is a rather precise question which has to do with the existence of certain kinds of operators in the CFT. And that's what these paradoxes are about. So today I'll mostly try and talk about paradoxes. Tomorrow I'll talk about resolutions, and I'll say that it is indeed possible to resolve these paradoxes, provided we keep some lessons in mind, and these are broader lessons for quantum gravity. And one of them is that the notion of a bulk spacetime, a local bulk spacetime, breaks down if you try and examine it too closely, if you try and look at correlators at too high precision, or if you look at correlators with too many insertions. And the second, this one actually I'll even talk about today because it's an obvious point that we hear many times. But the second point is that I'll say that the operators that you use to describe the degrees of freedom in the interior of the black hole might depend on the state of the black hole. And if you go to some other microstate of the black hole, the operators that you use to describe what you would call the same physical degrees of freedom might be different. And I'll talk about this tomorrow. So this is my one way to think of the information paradox. I like to think of it as follows. There's what I call the old information paradox. Old means more than 5 years old. So 2009 and before that. And so there's the old information paradox. And then recently there was this led to these paradoxes involving the strong subadditivity of entropy, which is when the interest in all of this started, which was about 2009 to 2012. But these paradoxes, as I'll show you, even though they're the ones which most people know about, if you ask most high energy theorists what the information paradox is, they tell you about this, and if you ask them about recent developments, they might tell you about the strong subadditivity paradox. But in fact, these are the weakest versions of these paradoxes, and they're easily resolved if you recognize that there are limits on locality. But there are more recent and more robust versions of these paradoxes. And these have to do with, as I said, the existence of local operators in AdS CFT, and I call this the modern information paradox. And the other thing I want to point out is that these versions of the paradox exist not only for single-sided black holes, but even for eternal black holes. Even for eternal black holes in AdS, which is a system that we think we understand well. And the resolution to these is more subtle, and I'll talk about this resolution tomorrow. So this is roughly the structure of how to think of how I think of the information paradox. So this is an overview of my talk. I'll start with some general review of black holes, just to remind all of you of some basic facts. And then I'll talk about what I already call the old information paradox and the strong subadditivity paradox, and then these modern versions of the information paradox, and finally about the eternal black hole, which is an important addition because it's it's a question of a system that, as I said, we think we understand pretty well. Okay. So let me start by reviewing some basic things about black holes. The first thing to remember is just about the horizon. So as all of you know, the black hole horizon separates the inside of the black hole from the outside. And sometimes when you look at pictures of black holes, you look at these pictures that you get in the media of black holes. They tell you about how this black hole is it's very big, and it's a very violent black hole and has all these phenomena that are happening about the black hole. But in fact, as we know, that's the wrong way to think about black holes. And this is an important thing to remember for all of this talk, which is that there's a very robust prediction from classical general relativity which is that if you look at the horizon of a big black hole, the bigger the black hole, the more sedate the horizon. So the horizon of a big black hole is a region that locally looks very close to being flat space, and this is something which is very important to remember. And there's a way to see this more precisely, which is to compute the Riemann tensor near the horizon. And the Riemann tensor tells you how nearby geodesics accelerate. So if you have some two observers who are separated by some distance d, the acceleration of these observers is down by 1 over m squared, where m is the mass of the black hole. So if m is very large, then these observers basically think that they're living in flat space. Their trajectories don't accelerate at all. And this is an important fact to remember. In fact, this is one of the central things, which will play a role in this, and it's an elementary fact, but important to keep in mind. As I said, so horizons are really global properties. They're not local properties of the space-time. And you have some observer, and this is some falling matter which collapses to form a black hole. This is the Penrose diagram you get. You have some observer who falls from outside to inside. This is the world line of the observer. The observer doesn't know when she or he has crossed the horizon. Okay. Now, in the early 70s, it was found that horizons, obey other properties, other interesting properties. And these properties are what go under the name of black hole thermodynamics. And just like in thermodynamics, there's the first law of thermodynamics, the second law of thermodynamics, such that du is TdS, and that the entropy always increases in any physical process. There's similar experiments you can do with black holes, where you can try and throw things into black holes, and you find that the increase in the mass is always proportional to the increase in the area with a constant of proportionality that's called the surface gravity of the black hole. And in any classical process, you can only add to the area of a black hole, you can't reduce that area. So that's like the second law of black hole thermodynamics. Of course, as we know, when quantum mechanics is added, it turns out that this is not quite right. And in fact, black holes are not quite black. And this was Hawking's famous discovery. And it turns out, in fact, that black holes emit particles. And one heuristic way to think about it, I'll talk about much more precise versions later in this talk, but a heuristic way to think about it, which is not a bad way in the end to think about it, is to think of pair creation happening at the horizon, and one of the pair goes out, the other pair falls into the black hole, and some asymptotic observer sees this particle, and so thinks that the black hole is emitting particles. And of course, there's this analogy with thermodynamics, and this notion of pair creation is not just some heuristic analogy, but rather Hawking calculated and found that black holes emit as things with a temperature, and the temperature is proportional to the surface gravity by 2 pi. And correspondingly, if you go back to this first law of thermodynamics, you find that you should associate an entropy with the black hole, which is 1/4 of the area, which is something that we use quite often. Okay. Now, something which I think we should keep in mind, and often people who work in this area also forget, has to do with the numbers that are involved. So, if you take a black hole of mass m, you can compute its surface gravity and you can compute its temperature. We usually put h bar and c to 1, but if you restore these factors, you get these factors of h bar, c, and the Boltzmann constant. And it turns out that the sun, if it was to turn into a black hole, would have a mass of about 6 into 10 to the minus 8 Kelvin. And if you have a smaller black hole that's hotter, you have a bigger black hole that's 1 billion times the mass of the sun, it would have a temperature that's 1 billion times smaller than this. And these are, of course, extremely small temperatures, much smaller than the cosmic microwave background radiation. And therefore, the temperatures of astrophysical black holes are very small, and this is the reason we haven't seen Hawking radiation, is because of these numbers involved here. Okay. The second thing to remember about black holes, and I'll come back to numbers, is that black holes lose mass through Hawking radiation because you have to conserve energy. And the loss in mass is just the Stephen-Boltzmann law. So, it's the fact that the loss in mass is sigma t to the 4 into a. And if you remember that t is 1 by m and a is m squared because the radius is proportional to m, you find that the rate of loss of mass is 1 over m squared, and therefore the lifetime of the black hole in 4 dimensions scales like m cubed. Okay, so black holes live for a lifetime that's proportional to the cube of the initial mass that they have. It's again useful to think of numbers. In fact, for a solar mass black hole, the lifetime of the black hole is 10 to the 67 years, okay, which is much longer than the age of the universe. But it's true because because it scales like the cube of the mass. If you think of a much smaller black hole, these things can evaporate much faster. And yet here, so nothing prevents us from thinking about much smaller black holes. So if you take the flights that we all came on here, and we turn those flights into black holes instantaneously, then these airplanes which have a mass of about 400 tons would evaporate in about 5 seconds. So if you have an ultra-powerful civilization that would turn airplanes into black holes and allow them to evaporate, you could do these experiments in your lab in reasonable lifetime in 5 seconds. Okay, but leaving aside these numbers, even though these scales are very different from everyday objects, there's a principle of the story, and that's the principle I want to stick to since I'm a theorist. And the principle is that even though black holes have very different scales, in principle they behave like thermodynamic objects. And therefore, in principle, from the point of view of thermodynamics, there isn't any difference between this fancy black hole and this burning coal. Both of them, they evaporate and they lose radiation. Of course, one takes much longer, one takes much shorter. But this is the principle, and this is something that we will keep in mind. Okay, so that was my black hole redux. I'm now going to go on to the information paradox. Are there any questions about this very elementary diagram material? Okay, so now the moment you start thinking of Hawking radiation, you come to what I would call the old information paradox, which is the following statement. You can take a black hole, and as I said, we could take these airplanes and combine them into black holes, but the airplanes could have different kinds of people with their different kinds of baggage and all sorts of things. And of course, what comes out in the end is just black body radiation. Right? So, what happened to all the information that existed in the airplane and all the engineering that existed in the airplane? Where did all that information go? And it looks like, if you really believe the story of Hawking radiation and of this black body radiation, then it looks like you take input A, you collapse it into a black hole, and you take input B and you collapse that into a black hole, and out comes black body radiation in both settings. So you have you give whatever input you like, you collapse it into a black hole, and the black hole turns it into perfectly black body radiation. And there's another way to say this, which is sometimes you can take a small black hole, you can throw a library into it. The black hole eats up the library, becomes a big black hole. After some time it evaporates, you've gone back to a small black hole, and you have radiation. And so it looks like the black hole is functioning as a perfect shredder. It takes the library and it completely destroys all the information in the library. It just gives you radiation, converts the library perfectly into radiation. And if this was really the case, then it would be in conflict with a very fundamental property in physics, which is the notion of reversibility. Now you take a ball, you throw it this way, and you reverse its velocity, and it goes the other way. So given initial data at any one time, you should be able to evolve, the Schrödinger equation given the wave function at one time, and of course in classical mechanics, given data at one point of time, you should be able to evolve it forward and backward in time. And if black holes really function as perfect shredders, that would be in conflict with reversibility, and that would be a serious problem for quantum mechanics. So that is what's called the old information paradox. Okay, so there's a resolution to this, which is actually the standard resolution. So I want to say that this is not really a paradox. It's very easy to resolve this paradox. The standard resolution, which was made precise by Maldacena in 2001, which was probably understood even earlier, was that you can have very small corrections to Hawking radiation, and if you have very small corrections to Hawking radiations, and how small do these corrections have to be? They have to be of order e to the minus s, where s is the entropy of the black hole. Okay, so if you have a very big black hole, then these corrections have to be exponentially small in their entropy, and these corrections can restore unitarity to Hawking radiation. And there's a precise way to say this, which is that it could be, you can take a pure density matrix, and provided you look only at simple observables or at coarse-grained observables, the pure state can look exactly like a thermal state up to corrections of size e to the minus s. So this is something that you might be familiar with in statistical mechanics. Now if you take the gas in this room and you have some observer, local observer who is doing experiments of two-point correlators or measuring the local pressure and temperature in this room, you cannot actually tell whether this room is in a pure state or if it's entangled with the rest of the world outside. In fact, for a very large class of observables, unless you start probing things very precisely, the local and the coarse-grained variables, experiments that you will do will be exactly the same for a generic pure state as they will be for a thermal state. So this is just a basic fact in statistical mechanics, and it's easy to construct examples of pure density matrices that have this property. Okay. And really what Hawking's calculation is telling us is that some properties of the final state of the black hole look thermal. In particular, if you measure low point correlators of the graviton field, you have some other are the fields in the universe, and you measure some 2-point and 3-point correlators of these fields, these correlators look like they're thermal. Okay, so what Hawking computed, in fact, was some 2-point function. And it's true that that 2-point function looks like it is a thermal 2-point function, but that doesn't mean that the final state is thermal. In fact, the final state is pure, and this is perfectly consistent, because a pure state can mimic a thermal state up to very high accuracy, and this is just an elementary fact in statistical mechanics. If you take a system with a Hilbert space of size e to the s, then the pure state in that system can look exactly like a thermal state for a very large class of observables.
This is only true for the thermal state, or for any mixed state?
No, so mixed state, what do you mean by any mixed state?
Some random density matrix.
Well, so usually a pure state, if you pick it from a certain energy class, actually resembles a microcanonical ensemble, but by the equivalence of ensembles, the microcanonical ensemble resembles a thermal ensemble. So it's not true that, pure states don't resemble any mixed state you can pick. Pure states happen to resemble, in fact, the microcanonical density matrix, which is close to the thermal density matrix. Okay, so there's, I'm just repeating the same statement. You can take, one way to say what I said is you can take the thermal density matrix and you can activate some corrections of size e to the minus s, and you can get a pure density matrix, which is just a restatement of what I said previously in terms of expectation values of observables. And this is pure, of course. By pure I mean that it squares to itself. That's the definition of a pure density matrix. And there's a slogan that goes along with this. The slogan that goes along with this is that information can be encoded in very small correlations of the Hawking quanta. Now it could be that one particle goes in one direction and another particle has a very, very tiny, exponentially small correlation with this particle and with all other particles. And these correlations are enough because there are so many particles that are emitted, and because the final Hilbert space is so large, these correlations are enough to preserve all the information that went into the black hole. So if you were powerful enough to collect all of these particles, you would be able to reverse the evolution. So this is the way the old information paradox is resolved. In fact, there's a reason why you expect such corrections. And so sometimes people say, oh, I'm going to compute this correction matrix, and they tried a lot in the old days to try and sit down and come up with models where they could compute, 1 over s corrections and 1 over s squared corrections, and try and add back reaction to Hawking radiation to see whether you can restore unitarity. But really, this is, there's no need to do this. And what is more, a process of this kind is, it's basically unnecessary, and it's not likely to succeed. And the reason is that these e to the minus s corrections, which are what are important and which are all that are necessary to restore unitarity, are non-perturbative. And the way you see that is you recognize that when you formulate quantum gravity, you should really formulate it through a path integral by doing a sum over all kinds of geometries with given asymptotic boundary conditions. And when you formulate gravity in this way, you can ask what is the black hole solution? When you say that there is classically a black hole, or there is a certain classical solution, what is it that you mean? And what you mean is that there is a saddle point of this path integral that has the classical geometry that you're talking about. Okay? And everything that you do, including perturbative quantum field theory about a fixed space-time background, or perturbative quantum field theory with back reaction added up to 11th order, if you could do it, all of that would eventually be an asymptotic series expansion of this path integral about this saddle point. Okay, so that's just a general understanding of how quantum mechanics and quantum field theory works. And if you now start asking questions of e to the minus s, you start asking questions which are accurate to that extent, then the very notion of a local space-time breaks down, because you can't work in the saddle point approximation anymore. And if you can't work in the saddle point approximation, then you don't have a notion of a local space-time. And therefore, these non-perturbative corrections, if they are required, to preserve unitarity, then we can just postulate that they're there, and no effective field theory calculation using up to whatever order, 11th, 12th, or 13th order, or 100th order in perturbation theory, can rule these calculations out, can rule out these corrections, and that's because effective field theory just is not powerful enough to rule out whether or not these e to the minus s corrections exist. And there's another slogan that goes along with that, which is that Hawking's calculation is not precise enough to lead to a paradox. Okay, very small corrections can restore unitarity, and the Hawking calculation is not precise enough to lead to a paradox. So there really isn't a paradox if you try and phrase the information paradox this way. Okay, so that's the first point that I wanted to make. And that's why I call it the old information paradox. Before I go on to the further in the talk, are there any questions about this? And this is an important point, because this is usually how people understand the information paradox. In fact, there is no paradox if you think of just Hawking's calculation.
Maybe I missed, but how did you argue for the non-perturbative nature of this correction?
No, I didn't. I didn't argue that the corrections were there. What I said was that what Hawking's calculation can do is tell you that the final state is thermal. And maybe it can tell you the final state looks thermal for, not, it can't tell you final state is thermal, it can tell you the final state looks thermal up to leading order and perturbation theory, or maybe first 1 by s or 1 by s squared or so on. But it can never actually control these e to the minus s corrections.
No, but e to the minus s would be non-perturbative?
E to the minus s is non-perturbative corrections.
Where s is entropy.
Where s is, well, so you have to be careful about what the value of the saddle point is, but everything scales the same way. So let's take s to be the entropy. So it's there may be some numerical factor, but e to the minus s is non-perturbative. And so, all you can do if you did Hawking's calculation and if you corrected it using back reaction, is you would be able to say that correlation functions of some low point operators look thermal up to some order in the 1 over s expansion. But that is not enough to tell you that the final state is thermal, because e to the minus s corrections are enough to unitrize a final state. Final states and pure states differ only by e to the minus s. And there's no way, you can actually check by doing Hawking's calculation or adding back reaction whether the final state is thermal. What you can check is that certain observables look thermal up to some order in the 1 over s expansion. And therefore the calculation is not precise enough to lead to a paradox. And if you believe that quantum mechanics should hold, which you should, there's no reason why this calculation of some 1 over s power series should lead you to abandon quantum mechanics.
But that's not a constructive answer, and I thought people want a constructive answer.
Well, I don't think a constructive answer of this kind is even possible, because the question of a constructive answer is trying to say, what are the e to the minus s corrections that fix this calculation? And those e to the minus s corrections almost certainly do not have a local interpretation. So it's really like, so I don't know what it means when people say they want a constructive answer. There is no, yeah.
I thought people want to actually see in what correlation this
right, but they can't see because
I think that's impossible.
I think it's impossible because if you wanted to see these e to the minus s connections, you would explicitly have to go beyond all orders in perturbation theory and quantum gravity. So the best way to see it really is to formulate things in AdS CFT and say that the CFT is unitary. Now, if you want to really do a bulk calculation, you would reach a point where the bulk spacetime doesn't make any sense. So I think that it's a hopeless aim to try and see it, and I don't think there's a paradox to start with.
So why couldn't there be a most important subleading saddle point? If you wanted to ask the question, if you wanted to do a pathological calculation of
there could be. So that's what Martesena's answer was, that there's if you think of so Martesena had a particular formulation of this, by the way, which was to say that you can phrase the information paradox in terms of quasi-normal modes, because quasi-normal modes have a property that they tend to decay, and if you follow quasi-normal modes for a time which is longer than s, then these modes get an amplitude which is smaller than e to the minus s, and just the long-time average of a correlation function always has to be larger than e to the minus s, because eventually it receives random corrections which fix it about e to the minus s. And Martesena said, oh, okay, so this correlation function is unitized by the other saddle point, which is not a black hole but some gas of gravitons. And so he said, here's an e to the minus s correction that can unitize and can resolve this particular version of the paradox. So it could be that happens, but it's not necessary. It could be that there is no local saddle point, and that would be fine as well.
That would be fine, but it would mean that the explanation you just gave isn't the right explanation.
No, the explanation I gave is still okay, because it still says that anything you do within local effective field theory cannot capture those e to the minus s corrections. If you're very clever and you have some other way to capture those e to the minus s corrections, that's great. If you can't capture them, even then there is no paradox. Because unless you can compute and tell me that those e to the minus s corrections are in contradiction with unitarity, there's no paradox. So and there is usually no way you can control those e to the minus s corrections.
I don't think that last statement is correct.
I think it is. Sorry, what do you mean? There is no sense in which locally you can control e to the minus s corrections, because the notion of locality simply breaks down. So you just can't, by doing perturbative quantum field theory, control all.
We can't do S matrix calculations.
Right.
don't we just need like an asymptotic boundary or space?
So you could do, so I think that you could do, so I think the best way you would have of defining an S matrix would be using the boundary CFT. But it's not all clear to me that you can do an S matrix calculation and get it right up to accuracy e to the minus s.
No, but your phrase was, well, I can't even ask the question in principle. Right. The point is, I can talk about an S matrix calculation in principle. I may not be able to do the calculation. That may be hard. But if I really could grind this thing out, I would see, residences and stuff like that.
So you would never be able to grind this thing out using bulk locality. You would never be able to, what you'd be able to do if you did this S matrix calculation is you would discover holography, and then you would have some holographic calculation of the S matrix, but bulk locality is explicitly the wrong thing to do if you want to get the S matrix accuracy e to the minus s. So if you want to get CFT correlators correct up to accuracy e to the minus n squared, you should explicitly not be using bulk AdS. You should be using just a CFT and computing cycle AdS.
Let's just work in flat space.
I beg your pardon?
AdS is using that.
You could work in flat space, and I can give you an argument why even in flat space, you would not be able to use locality, which I can give you the argument right now.
Locality. You are.
What do you mean if you could, how do you compute the bulk S matrix? Is there
in state, I have an out state, I have a matrix element that goes between them.
Is there a sense in which you could, is there a sense, there's a sense in which you may be able to define quantum gravity holographically, but there's no sense in which you can use a bulk. I think that there's certainly a sense in which we have a holographic description of quantum gravity, and those descriptions always respect unitarity. But there's no way you can take Hawking's calculation and correct it, get all of those e to the minus s corrections.
Why are you so sure that that's true? You're just asserting that. You're not supporting.
No, I'm saying that bulk perturbation theory breaks down, and so you don't know how to do quantum gravity beyond that.
It doesn't matter.
But bulk locality breaks down. So how are you going to compute these connections?
By including the contributions of other saddle points in principle.
By including the contribution of all possible asymptotic geometries in the middle,
they may contribute hierarchically with only a finite number contributing at a given order of accuracy.
Okay,
that's how non-perturbative corrections are well understood to work in quantum theory.
I think first of all we certainly have no example where in quantum gravity we can do this.
You didn't say there was no example. You said you can't even in principle do it. You're making these grandiose statements about what can and can't be done without supporting any of them.
I think the point is that I think that any understanding we have of how to do quantum gravity is an understanding which is perturbative or it's holographic. So it's certainly true that you can compute things in holography, and it's certainly not true. We have no example, but okay, if you can find an example and you control these e to the minus s corrections, then we would have a paradox. But I don't think we'll have that for a long time, and in fact, we may never have that at all because it's not clear that something like this should even make sense. That there should be some independent definition of quantum gravity which is not holographic. And the point here is actually this: it's that Hawking's calculation and any extensions of Hawking's calculation are not enough to get the paradox. So you can quibble on the precise statements I said and talk about how they're grandiose, but the statement here is perfectly precise and it's correct. Okay, are there any other questions about this? Okay, so the situation changed in a few years ago, and it changed with Mathur's work. And Mathur was the one who first tried to argue that small corrections are not enough to fix the information paradox. And Mathur's work led to what's called the strong subadditivity paradox, which I want to describe. So it's an attempt to say that these e to the minus s corrections are not enough to fix the paradox, and that this answer that I just gave is too quick. And in fact, you can try and phrase the paradox in a way where you can argue that there's an order 1 contradiction and not some small contradiction. Okay. So let me try and describe what the strong subadditivity paradox is. The key to the strong subadditivity paradox is to basically think of an evaporating black hole, and is to think of 3 subsystems. And so you take a black hole, and you allow it to evaporate, to radiate, and then you think of the radiation that was emitted a long time back, and for lack of imagination, I'll call that the system A. So there's a black hole, it's been emitting some particles, and this is the system A. And then this black hole continues to evaporate, and so now I want to think of a Hawking quanta that's just been emitted, and I want to call that the system B. And as I said, the way to think of Hawking radiation is to think of it in terms of pair creation. I'll give you something more precise later in this talk. There's a way to think of it in terms of pair creation, and the the partner of this particle that's being emitted is the system C. Okay, so just try and keep in mind these ADC. I apologize for